Okay, let's get started. So today we will keep discussing firewall. So Wednesday, we talked about one kind of firewall, packet filter. We discussed what kind of operations it can do. So today we are going to show some concrete examples using the iptables. So first of all, a firewall is just the first line of defense. It's not perfect. So using a firewall is kind of like living in a gated community. Yeah.
It's kind of like looking on the lecture. So, is there a difference between the Security Association firewall, or SPD?
So the Security Association was a concept in IPsec.
Right.
So it has nothing to do with the firewall.
I mean, does it kind of operate similar? Because it seems like they both have like policies that keep stuff out.
So policy is like a very high level idea in security. Policy is like what do you want for your network, right? Or what do you want for your system? But there are mechanisms to network power and enforce those policies. So firewall is not perfect for many reasons. First, usually firewalls, they only look at certain fields at the transport layer and the internet layer. It usually do not look at your application payload. And like we discussed Wednesday, even if you are using firewall, your network is still vulnerable to IP address spoofing. So even though firewall can stop limited cases of IP spoofing, but usually they cannot stop IP spoofing. And the firewall, there are some way to bypass firewall as well. So there is an attack called the tiny fragment attack. Basically, what we do in this attack is the attacker will split the IP headers over several very tiny IP packets. So the firewall, if the firewall is a stateless, it only looks at each packet. It cannot even see the whole TCP headers. It cannot see the whole transport layer headers. So in those cases, they can bypass the firewalls based on port numbers and those informations. So the solution is either the firewall can discuss, it can just drop all the packets that is fragmented, or they have to remember those packets, reassemble those packets before checking. Also, firewall can generate a lot of logs. So like an organization like SU, so our firewall may take millions of queries every day, and even 1% of packets generate one log entry that would be 10,000 entries. So it's infeasible for any human administrators to check all those logs. But if we do not log those information, we may not able to find some suspicious things we want to know. So today we are going to look at a very concrete real-world firewall called iptables. So basically, iptables is a Linux stateful packet filtering firewall, and it uses this kernel module called netfilter to perform filtering of network packets. So iptables is not the only application use this kernel module. So there are optables that handles kind of like a data link layer firewall, and there are IPv6 tables to handle IPv6 firewall, and contract, which is a module to maintain the status of TCP collections. So contract is also used by iptables because iptables is a stateful firewall. And underlying, they all use this netfilter kernel module. So you actually have been using this tool, iptables. So the tool you are using, what you did is you sudo and iptables and give some parameters, And this IP table you were using is just the user space utility of that IP table and also the net filters. So before the development of IP tables, there were several other firewalls for Linux. The Linux kernel 2.0 came with a firewall called IP Firewall Administrator. Then later 2.2, they have IP chains, and IP tables were developed on top of this IP chains. So in November 1999, they started a development team to work on this IP tables. So it has been almost 17 years. So they are going to replace IP tables and net filters, actually. So 2 years ago, the Linux 3.13, it comes with a new kernel module, not a net filter, another kernel module called NFT tables. And this NFT tables is replacing a net filter. But if you are using Linux now, you have both of them. And this NFT tables is configured via just one user space utility called NFT. But if you are using net filter as the underlying module, there are several utilities: IP tables, IPv6 tables, iptables, just like we discussed. So I have a question for you. So because this IP tables, it's a Linux application. So does that mean it is a host-based firewall? Does that mean it's an edge firewall? It can only protect your local system?
What was the question?
So IP tables becomes with Linux, right? But does that mean it's not a network firewall? It is only a host-based firewall. So
yes. Is it? Like, is it just a host base?
that's my question.
Okay. Yes, it is.
You think it is?
Probably not, because Linux can run on all sorts of
Yes. So that's correct. So basically, it depends on how you use your Linux system. So your Linux system, you can use it on routers. You can use it as one router. So basically, in NAV1, what we did is we have a network like this. We have a gateway which runs Ubuntu and a client and a server. Both of them also run Ubuntu, and only the gateway has the internet access. So the first thing you did in NAV1 was to enable the IP forwarding at the gateway. So by enable IP forwarding, you are making this gateway literally a gateway, a router. So even though it's just a regular Ubuntu system, it actually runs as a router. So IP tables can be a edge firewall, can also be a network firewall. Depends on how you use your Linux system. And IP table has very flexible design to support all those usages. So in order to support that, IP table has 5 built-in chains. And basically, those chains, they reside at one point in the kernel's network package processing path. For example, if you have a package coming into your system, that package will first, the system will decide if this package is for me, or I am the router, I should route this packet. Or if the package is for me, the system will process that packet, check the IP headers and the TCP headers, and decide to which process I should give this packet to. And if any application, in here the system is more like an application, wants to send out a packet, it will add some IP headers, and it will go out through your network card. And if your system is a router, then the packet will be forwarded to maybe another, from one network card to another network card. So to support that, iptables, they have 5 built-in chains, and it's called pre-routing, input, forward, post-routing, and output. So basically, the chain determines when a packet is exempt. So if we have an incoming packet from outside of this host, and our system is not a router, our system is a host system, then that packet will be processed by rules in the pre-routing and input chains. So basically, one chain is a set of firewall rules or other rules, may not be firewall rules. And if we are sending out a packet, so all those packets, they will be processed only by the output chain and the post-routing chain. And if your system is acting like a router, like the gateway in NAT1, and all those packets go through that router, will go through the iptable pre-routing chain, forward chain, and post-routing chains. So all those chains, and or some of the chains, they can be empty, which means we are not specifying any rules in those chains. For example, this is a screenshot I got. So we do iptable L, which lists all the chains on our system. And you can see here that we have 3 chains, input, forward, and output, and they are all empty. There is no policy, there is no rules in these chains. And since there is no rules, we can specify the default action for the packets. And in this case, the default action is just accept. So all the packets, they do go through the iptables, but the iptable, in this case, is not really doing anything, just accepting it, not rejecting. But also, here we can see that this system, the input chain has processed 11 gigabyte data, and the forward chain didn't process any data, so maybe this is a screenshot taken from a host, not a router. And the output chain generates more data, 16 gigabyte. So maybe this is a web server or something. So besides those chains, iptable also has another way to group rules that is called tables. So basically, chains is a way to group the rules based on when to process them. And the tables is another way to group rules based on what kind of actions are valid for each rules. There are basically 4 tables. One is called a filter, and this is a default table, usually used for filtering packets. And you can imagine, so the action there would be accept or drop, and there is a network address translation table. So in order to translate the network address, you need to modify the TCP, the IP and TCP headers. So basically, rules in this table, they will change the TCP headers, and the rules in filters, they are not supposed to do that. And there are other rules in Mango and raw tables, which offers more powerful actions, such as sending back ICMP message or change other fields, something like that. So if we put them together, we have a detailed packet path. So this is a network. So whenever a packet comes in, the network, the packet is first processed by this pre-routing chain raw table, then the pre-routing chain Mango table, pre-routing chain NAT table. Then your system will decide how can I route it, or if I should route it. If the system decides to route it, it will go to the forward chain Mango table and forward chain filter table, and go back to your system, and the system decides I'm going to send it out. Then it will go to the post-routing chain Mango table, post the routing chain NAT table. So if the system says this is a package for one of the applications on my system, it will go this route instead. So you can see that. So basically there are several chains, 5 chains, and the chains is like different choke point in the system kernel and decide when to process a packet. And the tables, like a raw, mango, or NAT, they are just a way in those chains to organize different rules based on the actions available. Any questions so far? So we are going to see some concrete examples of how to use these IP tables. So if you want to add any rules or delete any rule to IP table, first you need to specify which chain you want to change. And you can either insert to the chain or append to the chain. That makes a big difference. So insert will put a rule at the top of that chain, and append will put the rule at the bottom of that chain. Like we discussed in Wednesday, firewall rules are following the principle of a first match. So only the action of the rule that matches the packet first will be enforced. So the order of the rules is important. So whenever you insert or append, anyway, you want to add some rules to existing firewall rules, you need to decide where I want to add these rules. And you can also specify which table you want to use, but this is optional. If you do not specify, then which means you are using the default table, which is the filter table. And then you need to specify the rule specs. So basically the specs has 2 parts. First is matches, the second part is target. And target is just the action, like accept, drop, the action you want your system to enforce when the packet matches some rules. And the matches can specify the TCP header fields or TCP states. So you can use it to match firewall rules. So if a packet doesn't match any match in this chain, so the packet will one rule. So the packet will be sent to the next rule in the chain to verify. And if a packet meets the matches, then the action will be enforced. And the target types, the action types, depends on the type of the table, like we discussed. So the filter table acts like a firewall, so you can accept a packet, you can drop a packet, you can return a packet, which means you will send out an ICMP message to notify the sender that I cannot accept your packet. So drop, the system will just silently drop that packet. And a network address translation table will have different actions. So IP table, even though it is a stateful firewall, it offers something more than a firewall. You can use it to accept, drop packets, and you can also use it to change packets. So like I said, there is you can add rules to the head of a chain, you can append a rule to the tail of the chain, and you can also use this to delete a rule or replace a rule. Yes?
What was that, DNet and SNet from the previous one?
I'm not sure. Some dynamic network address translation.
They're all static.
And then static.
Yes, but I'm not sure how it works. So what you used in M1 is just this one. This is like the default, just do the regular translation. So in that rule specs, you can specify all the fields in the IP headers and the TCP headers, transport layer headers to match a packet. So it could be the protocol number, source address, destination address, also input interface, output interface, and if this one is fragmented at IP layer, and also TCP flags, and more importantly is the collection state. So the collection state can be new, established, and with this collection state, we can actually provide a stateful firewall. Without this, this is just a stateless firewall. So we are going to show one example to say how it works. So this is the example we used in Lab 1. So we have the gateway connected to internet. So when you first log into the thought system, your gateway can already access the internet. But the client and the server, they do not have the access to internet. So what you did is you want to enable internet for client and the server. So the gateway, let's assume it is connected to internet through this Ethernet 0, and the Ethernet 1 connect to client, and the Ethernet interface 2 connect to the server. So the first thing you did is enable IP forwarding. So on the gateway, so the gateway can act as a router. It can forward a packet for any other machines. Then what you did, so this is the command you use. This is the line in the configuration file you used to enable IP forwarding. So you enable IPv4 forwarding here. Then you did is you sudo iptables table net append post routing and out interface Ethernet 0, and the action is MySQL read. So basically what you did is by executing this command, you add one rule in this post routing chain and net table. So to enable that, your gateway to do network address translation for you. So why you are not doing it anywhere here? Because this is not a packet for your system. This is a packet you are supposed to forward. You are acting a router, so you can only do it here. And at this layer, there is no network address translation table. So you are supposed to do the network translation after how the system decided to route it. So that's why you are inserting this rule in this chain, this table. Then what you did next is you append the forward to the forward chain, and you're not giving which table it is, and you are saying the input interface in this case is Ethernet 1, and the action is accept. So basically, you are adding this rule to the forward chain and the filter table, because you're not specifying which table I want to use. So by adding this, any packet coming from Ethernet, the port number Ethernet 1, your system iptables will decide to accept it. So it will keep moving to the next chain, and next chain, and it will be translated by the network address translation table. So after doing this, the client will be able to access internet. Then you do the same thing for your server by just changing the input interface from Ethernet 1 to Ethernet 2. So basically, this is how you use this iptables. So we have a lab later for you to work on iptables. So in lab 1, we give you the command. So you just type in the command. You didn't really need to know how it works. But in that firewall lab, you are going to figure out how you should construct those commands. So one more thing is firewall is still, even though firewall has been there many, many years, 20 years, maybe even longer than that, it is still a relatively hot research area. There is still a lot of research going on firewall. For example, like I said, in firewall, the order of those rules matters because of the principle of first match. So whenever a packet comes into your firewall has to compare that packet to all those rules. And if there are thousands of rules, it can be very slow. So the reason you have to compare them is because the fields of those rules, they are kind of overlapped. So if one packet can match the first rule, it's still possible that it can match the second rule or the third. So if we can isolate those fields, so each rule, they specify different field space. There is no overlap between them. So we do not have to match each packet with each rule. We can do instead of doing a big OM comparison, we can do that at constant time. So what we in our lab we did before is we worked on this kind of problem. So we use some we call header space analysis to find the overlap in different policy rules, different firewall rules. That if there is an overlap, what we try to do is if there are two rules that have overlapped header space, then we try to split those overlapped space and making 3 rules or maybe 4 rules. So those 4 rules are still equivalent to the previous 2 rules. But by doing this, we don't have to do one-by-one matching because all those spaces, they are isolated, separated. So we can do that. So this can really speed up the firewall rule comparison. And another very interesting field of firewall research is related to the new network paradigm called software-defined networking. We also did something interesting there. So I will cover that when we talk about software-defined networking. So, so that's all for firewalls. Any questions? Okay, if there's no questions, good luck on the midterm on Monday.
Quick question.
Yeah.
So what
What?
map table? We didn't have to do anything with the true routing because the packets did come in, right?